Seismic analysis is very important for the stability and safety of any structure. If we design a structure in a moderate or high seismic prone area, seismic analysis results normally govern the reinforcement percentage or section size. And if we consider any high-rise structure, without a proper dynamic analysis, it is not possible to finalize the design or get approval. There are several factors which are significant for a static or dynamic analysis. Seismic weight or mass model is one of those. Do you know how to add a mass model in STAAD or how to avoid the common mistakes which can affect the seismic analysis? Hi, I am Surajit Ghosh, and in this video, I'll cover different methods available in STAAD to define seismic weight or mass model for static and dynamic analysis. Also, I will compare all these methods and let you know which one is the most suitable method of mass modeling for any concrete or steel structure. Before going into the details, I just want to discuss few points related to the seismic analysis and why seismic weight is so important. I'll consider both ASCE 7 and IS1893 code for this discussion. But if you follow any other code for seismic analysis, the logic remains same. Only few values or empirical formulas may vary depending on the code. Static seismic analysis using the approximate fundamental time period is the most basic approach, but several design codes don't recommend this method unless the structure is regular, height is not that significant, and located in a low seismic prone area. For example, if you consider IS 1893 Part 1 code, under clause 7.6, code clearly suggests not to perform static seismic analysis if the height of the structure is greater than 15 meter and located in any moderate or high seismic zone. Still, we need to perform static seismic analysis for different reasons, which I will discuss at the end of this session. During static seismic analysis, the horizontal seismic coefficient is first calculated and then it is multiplied by the overall seismic weight of the structure to calculate the base shear value. This design base shear is then distributed vertically along the height and along plan in each floor level. If we look at the force distribution equation, we can notice that it depends on the weight of the floor. So, if a floor has higher seismic weight, it attracts more seismic story shear. For static analysis, seismic weight is required only in the vertical direction, and we don't have to define any weight in other orthogonal direction. For dynamic analysis, we are concerned about the response of the structure for different modes, and the peak responses are combined using a modal combination method. In this case, as the whole structure is excited in all directions, so it is required to define the seismic mass in all the three global directions. Why mass model in all three directions is required for dynamic analysis, and what will happen if we don't define any mass in a direction, that I'll cover in another video. This proves why seismic weight plays an important role both for static and dynamic analysis. And I think it is clear now that if we don't create the mass model properly or define the seismic weight incorrectly, analysis results will be incorrect. Seismic weight of the structure and mass model is not same, and sometimes it might be confusing whether to define the weight or mass for seismic analysis. There is a difference between weight and mass. Mass is the measure of the amount of matter in a body. It is directionless and applies equally in all directions, whereas weight is a measure of how the force of gravity acts upon that mass. Weight is nothing but mass multiplied by the acceleration of gravity. For static seismic analysis, weight of the structure is used. If it is defined under seismic definition in kilonewton unit, then that is directly used during analysis. If we define it as a mass in kg unit, then program internally converts it to weight and then use that for seismic analysis. Just for an example, compare these two scenarios. In the first model, seismic weight is defined in kilonewton unit and total weight is used for base shear calculation. Whereas in the second model, seismic weight is defined as a mass and during analysis, it is converted to weight. For dynamic analysis, mass of the structure is used for analysis rather than the weight. Though mass is used, still we don't have to convert the loads manually to mass by dividing it with g, as STAAD converts it internally during analysis. If we define a load under any dynamic or mass reference load case in kilonewton, program internally converts this to mass by dividing the load value with g. So both for static and dynamic analysis, we can define the seismic mass as a load or weight. Finally, STAAD works with the lumped mass principle, where an applied load is converted into lumped mass during analysis. So if we apply a distributed load like a member load or self weight of the member, total load is calculated and that force is lumped at the end nodes of that member, plate or solid. Similarly, a concentrated load or patch load is converted to a lumped mass and applied at the end nodes. That's all about seismic mass and weight and how these are considered during analysis. Let's now discuss about the methods available in STAAD to define the seismic weight. First one is the traditional approach, which has been used for a long time. For static seismic analysis, we can add the weight under seismic definition. Only weight in the vertical direction can be specified here, and this is used to calculate the base shear value during static analysis. For dynamic analysis, this vertical seismic weight is not sufficient. We need to create a mass model with mass in all three orthogonal directions. We can define this mass model under the first primary load case, where the response spectra or time history load is added. For any subsequent dynamic load case, same mass model is used. No need to define it again and again for other dynamic load case. There is another method available using which we can define the seismic mass both for static and dynamic analysis. Using mass reference load case, we can add a mass model under a mass reference load case, and during static or dynamic analysis, seismic weight is calculated directly from this load case. This is the easiest approach as we don't have to define separate weight for static and dynamic analysis. Let's find out what are the advantage and disadvantage of each method and which one provides the best solution. I will use this G+14 story building to discuss all these methods. First, I will prepare this model for static seismic analysis. Though this method is not right as the height of this building is greater than 15 meter. I have already created few primary load cases, one dead, one live and one roof live load case. Static seismic loads are also added to the model as the first two load cases. Obviously, perform analysis and change command is added after each of these seismic load cases. Why it is required? That you can check from my previous video on modeling for seismic analysis. For this structure, I want to perform static seismic analysis as per IS1893 Part 1 2016 code. I have already defined all the seismic parameters required for this model, including structure type, zone factor, response reduction and importance factor. These values will be used to calculate the horizontal acceleration coefficient AH. To define the seismic weight in the vertical direction, we can use this weight option available here. Normally, under seismic weight, full dead load is considered along with partial live load. Live load percentage depends on relevant design code. For example, under clause 7.3 of IS1893, code suggests to consider 25% of live load with load intensity less than 3 and no roof live load. So, depending on the code, we need to add the reduced live load in seismic weight. Though we have already defined the gravity loads under different primary load case, still using traditional approach, we cannot reuse these loads to define seismic weight, and we need to add each of these gravity loads again. For example, we have applied the external and internal wall load as UDL on these members along with the slab weight and floor finish load, and now we need to assign these loads from seismic weight page. To specify external wall weight, we can select the member weight with load type uniform, specify the weight as a positive number, and assign this to all the relevant members, which is really time consuming. We need to isolate the members from primary load case unless there is a separate member group. What happens if we try to copy paste these loads from a primary load case using the input editor? We can do it, but there is one problem. The load syntax are different. Check this UDL. See, the load syntax of seismic weight does not match with the same load defined under a primary load case. So if we try to copy paste the load from a primary load case to seismic definition, we need to manually change the syntax. This is both time consuming and prone to error. Not a good option. Next, I want to prepare this model for dynamic analysis. I have included two response spectra load in the X and Z direction using IS1893 code. All required inputs like the reduction factor, torsion, and signed response spectra inputs are specified. What is the purpose of each parameter in this window? That I will cover in another video. As discussed, we need to define the seismic mass in three orthogonal directions for dynamic analysis, which is also known as the mass model. Though we have already defined the seismic weight, that is only in the vertical direction. Hence, that will not be used for dynamic analysis. We need to define the mass model under the first dynamic load case, and this will be used for all dynamic load case. This is a repetition of job as we are defining the same load for the third time. This time we can use the input editor. We can copy the load items from the primary dead load case, say the first three load items, and paste these loads 3 times under the first dynamic load case. To apply the load from the X and Z direction, we need to modify the load direction from Y to X and then from Y to Z. There you go. The mass model is ready. Also note that it is better to change the load sign from minus to plus as this is the mass of the structure. I have only copied 3 load items and we need to repeat this for all the load items. For live load, we need to recalculate the load intensity by considering correct reduction factor like 0.25 for IS1893 code and change that. Do you think this is a good option? I don't. For static seismic analysis, we have modified the load syntax, and this time we are changing the load intensity as well as the directions. We have defined the same load thrice in different formats to perform a single task, seismic analysis. To eliminate all these duplicate works, another option is available in STAAD, which is known as the mass reference load. Under load definition, we can add any load under a reference load case, which does not take part in the analysis unless it is called from a primary load case. I have already discussed how to use a reference load case and how this can reduce the overall analysis time in my last video. You can check that for more details. When we create a new reference load case, we can select the load type like dead or live load. Along with that, there is a load type which is the mass reference load case. This load type is unique in the sense when you create a mass reference load case, program use this for seismic weight calculation. For static seismic analysis, we can define the weight in the y direction. If we define a mass model with loads in all three directions, then for static analysis, weight in the y direction will be used, and for dynamic analysis, mass in all three directions will be used. So it is valid both for static and dynamic analysis. And if we use a mass reference load case, we don't have to define the seismic weight anywhere else. We can simply define the seismic parameters for static seismic analysis and response spectral load for dynamic analysis. Program will read the relevant seismic weight directly from the mass reference load case and use it for static or dynamic analysis. In older version of STAAD, we need to create this mass reference load case manually. Either we can add the loads from the GUI, or we can open the input editor, copy the loads from dead and live load cases, and paste it directly under a mass reference load case without changing the syntax, similar to the mass model generation under a dynamic load case. That's all. Though a mass reference load eliminates multiple seismic weight definition, still we need some manual effort to generate the seismic weight. How about an automated process where we can reuse the gravity loads to form the mass model? Well, this option is finally available in STAAD since V22 Update 9. If you are using this version, then you may have noticed this mass model generator in the load page. Do you know how to use this option to auto-generate the mass model? To use this feature, we need to first add the gravity loads under primary or reference load case with proper load type like dead, live or snow load. Load type plays a vital role for mass model generation as this feature is linked with few specific load types and the default load factor depends on the load type. In this model, I have included all the gravity loads under dead and live load case. Though the seismic definition is created, no seismic weight is defined here as I want to use a mass reference load case. Two static seismic loads from the X and Z direction and two response spectral load case are also added in this model. No mass model is created under any dynamic load case. To generate the mass model for static and dynamic analysis, we can simply click on this tab. This will open the mass model generator window. From here, we can generate the mass model either under a mass reference load case or under the first dynamic load case. If there is no dynamic load present in the model, then this option will not work. Also, if we want to use the mass model for static seismic analysis, then we need to define it under a mass reference load case. For this model, we will add the mass under a reference load for static and dynamic analysis. Next, select the gravity load case which we want to consider for mass model generation. By default, all load types which are meant for lateral load like wind or seismic load are grayed out. Apart from these lateral loads, only few primary loads are used for mass model generation. For example, consider this sample model where I have included all types of load from dead, live to push, a load with type none, and when we open the mass model generator, only 6 loads are identified by the program which can be used for mass model generation. Except these 6 loads, all loads are grayed out, including the load with type none. Group live load is also ignored. Program automatically includes these eligible loads and assigns corresponding factor in the list. That's why load type plays a vital role for mass model generation. There are few additional rules which we can check from the help manual. Among these rules, few are very important, like only vertical loads are considered for mass model generation and load in any other direction, moments, loads applied in the local axis are ignored. What this means? If there are multiple load items under a primary load case, which we want to consider for mass model, then only those load items will be used which are in the global y direction or any projected load. Any other load item will be ignored. Also, several other loads like support displacement, area, temperature load will not be used to generate a mass model. You can check this document for more details. We can further change the load factor if required. For example, IS1893 code suggests to consider 25% of live load with load intensity less than 3. We can easily consider this and change the load factor for live load case. Once done, click on the Generate tab and see, entire mass model with mass in 3 orthogonal directions are added under a mass reference load case. Easy, right? This feature will obviously minimize our manual effort by generating the entire seismic mass in one click. Unfortunately, no option is available here to select the direction, so we cannot use this to generate seismic weight only in the y direction. For static seismic analysis, we can use this feature to generate a mass model. Program will use the vertical loads for seismic weight calculation. For example, consider these two models. In the first model, weight is defined under seismic definition, and in the second model, a mass model is generated with the same load intensity. From the output file, we can verify that for both these models, same seismic weight is considered to calculate the base shear. This proves that a mass model produces correct results for static seismic analysis. I think it is clear now that inclusion of a mass reference load is the easiest way to perform static or dynamic analysis. To summarize, if we want to perform seismic analysis, we can simply add static seismic parameters from seismic definition and add seismic load from the x and z direction under separate primary load case. For dynamic analysis, we need to add response spectra or time history loads. Next, we can reuse the gravity load data to generate the mass reference load case. Do you know, we need to add static seismic loads in the model though dynamic analysis is performed. This is required to compare the base shear values as suggested in clause 7.7.3 of IS1893 code, and if static seismic load is not available, then there might be some serious problem. I will cover this in my next video. For rest of the seismic analysis requirements, you can check my previous video on modeling for seismic analysis. There are few points that we need to keep in mind during seismic mass generation. For static seismic load, if we specify a mass reference load case along with the seismic weight under definition window, then program considers the seismic weight only from the seismic definition. Mass reference load case is not used for analysis, and a note is reported in the output file. Similarly, for dynamic analysis, if mass model is defined under a dynamic load case along with a mass reference load case, then seismic weight is considered from the dynamic load case. If mass model is defined under each dynamic load case, program considers the mass model specified under the first dynamic load, and other mass models are ignored. A warning with the load case number, which is considered for mass model, is reported in the output. If multiple mass reference load cases are specified, then program internally add all loads from multiple mass reference load cases, and total load is used as the seismic weight. One suggestion: do not define the seismic weight under seismic definition or mass model under a dynamic load case when a mass reference load case is already present in the model. This is an incorrect modeling approach. Do you know how to validate the seismic weight or mass information? For static analysis, seismic weight is reported in the output file in each direction. This is the total weight of the structure defined either under the seismic definition or under a mass reference load case. For dynamic analysis, a mass.txt file is generated and saved in the same folder with the same file name. In this file, all seismic weights or lumped mass are reported for each joint in each direction, along with the total mass in each direction. From this file, we can easily verify the seismic mass used in the dynamic analysis, or even apply this as a load in another model. That's all from me today on mass model generation for seismic analysis. If you are still using the tedious copy-paste method to generate seismic mass, then I'll recommend to use the new mass model generator, which can reduce your modeling time and remove any manual error. I hope you have enjoyed this session. Thanks for watching.